Okay, welcome back. In this lecture, we're going to talk about extrema on an interval. Now, this entire chapter in your textbook about extrema, minimums, maximums, these types of things, they're very important to me. So just keep that in mind for when you're studying and when you're thinking about what the first exam will look like. Because, well, the applications are everywhere for these types of topics. But more importantly, you need to have an understanding of the basic differentiation rules. There's no point in like having an exam over those things, right? So we'll have like a review of just the rules, and then we'll have a review about all of this stuff, this chapter, this section, the next section in this chapter before the first exam. But the main topics will be these things. So just a heads up. Okay. All right. So what do I mean by extreme? Well, the general idea that we're going to be working towards is that given some real valued function f, it might look something like this. Okay, so there's some curve like that. And we want to understand and provide terminology and techniques to locate these changes in direction of the graph, right? Here, the function is increasing and then it's decreasing, right? Here it's decreasing and then it's increasing. Knowing when these changes occur is important for many different reasons. To me, I think about the following problem. So the goal, I suppose, which isn't mentioned in your textbook, but this is my goal, would be to solve the following problem. Okay, so this is like a function. Okay. So what does this problem say? This is min f of x, there's an epsilon there for some reason, and r. So what this reads is, this reads as, so find the minimum value for f of x over all real x in the domain. Okay, so that's what this problem is more or less saying. Now, in the textbook, you'll see that there's minimum and maximum problems, but to me, they're the same thing, right? Minimizing f of x is the same thing as maximizing negative f of x. So I just generally think min, but there are these two sides to it, right? Now, this is taken over every possible x in the domain. That's the hard problem. This actually has a name. It's called unconstrained optimization. This is very difficult to solve, and we just can't solve it in general. Like, because we have no idea how this function is really going to behave everywhere else in general for like complex types of functions. So what we can do is restrict our domain to be of particular interest in size. For example, we can consider this problem over an interval, finding the minimum or maximum values over an interval. So here, right, like maybe I could say like A, B. Now this becomes possible to solve, right? So for example, it looks like the maximum value of the function occurs right there, and the minimum occurs right there. Right? So if we're seeking to solve this problem fully on an interval, we can do it if it's continuous. Okay? Now, if we consider all real x again, then who knows what's going to happen outside that interval, right? if it's some complex function. So then we could say at least like there's like a local, what we would call like a local maximum right there, or a local min right there, local min right there. Like locally, right? It's minimum. It's changing its direction from either decreasing to increasing or from increasing to decreasing. And these are what's called extrema, and when these things are changing. So let's go ahead and write down the formal definitions now that we'll be using in your textbook. Note that this is not, the terminology used in your textbook may differ, for example, from like this book. It will differ, but the general idea is the same. Okay, so just remember that. The idea is about these changes in direction and how to define them, and then also how to find them. So definition. Okay, so let f be defined on some interval I. Right, so for example, this closed interval AB, I should say closed interval when I'm doing this definition, but so like this right here, A to B inclusive, okay? But it also works on open intervals if you don't include the endpoint. So the idea is the same. So one, so f of c is a minimum of f on I if f of c is less than or equal to f of x for all x in I. Okay, so I should probably note when I was looking through your textbook, I saw that they use f of c is the minimum. That's incorrect. You can have plenty of minimum inside an interval, right? Like just imagine like it's like bouncing, and always attaining. That can happen. So I'm just going to say a minimum on that interval. Actually, to be clear that we're on an interval, I should highlight that this is the definition of that. Minimum f on that interval I. In a similar fashion, we can define a maximum. So f of c is a maximum of f on I if f of c is greater than or equal to f of x for all x in I. Okay. Now, so this is on a given interval, right? So if there exists an interval I where there's a minimum, if there exists an interval I where there's a maximum, then we would say that these are local minimum and maximum for the entire functions. Right, so if such an interval I exists, then these minimum and maximums are called local minimum and maximums of F. And I'll say on R, so on all real numbers. Okay. So again, like in an interval, there could be a unique maximum with respect to that interval. If such a thing exists, then you can at least say it's a local minimum or maximum for all possible values. That's a local max, local, right? And then if you look at like a little interval around that, then that'd be like a local minimum as well, right? So if for whatever reason you can determine that it's the minimum over all R, then it's a global minimum maximum. So I'll just add that. If f of c less than or equal to f of x for all x in R, then f of c is a global minimum of f, which does occur, right? But in general, it's difficult, right? So the idea is that yes, we need terminology for all possible values of R, which is the local and global, but in we can really ever hope to truly solve the problem on intervals. So there's just this overlapping use of terminology. Okay. So what would be a function where there's an obvious global minimum? A parabola, right? Any type of parabola is going to have a global minimum. Okay. Any type of parabola. In fact, there will, if you try to find any intervals other than around this, if you look at this interval right here, right? If you look at an open interval, I mean, right there, then if you look at the function's values, there is no minimum, there is no maximum, because you're not including the endpoints, right? So the only interval that would have such a thing would be something right there, and then there would be a possible minimum in the interval. Okay. So now parabolas have a global, that's an obvious one, but in general, let's focus back, and not in general, but let's get more specific back to these intervals, where we want to consider functions other than just parabolas and see what we can say. Well, it turns out that there is a theorem that can help us out. Okay, and this is called the extreme value theorem. Okay. So again, anytime you see a theorem with a name, it's important. Okay. So in this theorem states, if f is continuous, on the closed interval AB, then f has a minimum and maximum on AB. Okay. So like, why would this make sense? Right? Why would this make sense? Well, what do we know about continuous functions on closed interval? They attain every value between f of a and f of b, provided they, remember that theorem? Okay, like, if you have a closed interval a, b, and f of a is different than f of b, like that's like f of a, and then this is f of b, then every value in here, right, is going to be attained between a and b. This is not why this is true, but do you remember this concept, right? Like if we go here, we can like go up, down, but like we're going to take up all of those intervals, right? So the continuity means like the graph is somehow connected. Right? Do you remember that theorem? Continuity means that if I look at this point and that point right there, f of b, right? It's a connected graph in between them, right? That's actually the correct terminology. Well, if you draw the graph, it's connected, right? So then this isn't a proof of this statement, but it might help you understand why it's true. If the graph is connected, right? What else could, like, how could there not be a minimum? Right? How could there not be a minimum? It would be, because if you're on this closed interval, looking back over here to this open business here, right? Like if you're looking at every value of this function in that open interval, it's like open, open, there's no actual endpoints. But if those are contained in there, then there is like a minimum and a maximum. Because the graph is going to be connected. Like if I drew it, if this was closed instead, it looks like that. Right? So there is going to be at least a minimum maximum. Again, this is not a proof. I didn't want to go through the proof of this. It's not that bad. It's just applying the definition of the derivative. I mean, yeah, it's related, but does the idea make sense? The graph is connected, so what else could possibly happen? Okay. So now you know some pretty nice conditions where you can start searching for these minimums and maximums on closed intervals, right? At least closed intervals. Open intervals, you don't need. But closed intervals, we do. As long as that function is continuous, then we'll be all right. Okay. So, well, I was going to use this example from your book, but we already know the answer to this. Right. Let's consider the function f of x equals to x squared minus 4x plus 5 on the closed interval -1, comma 3. Now, last time I had a little tangent about fractions, right? This is a good example to revisit a technique from pre-calculus that you might have forgotten. Like, what type of graph is this? The graph of this is what? It's a parabola, right? How would we plot this thing? Okay, so yes, very carefully would work. But what's the easiest way to plot a parabola? Like there is a form, right? There's this like vertex form of a parabola, right? Y'all remember this? Vertex form? Do you remember this thing called completing the square? Okay, so this is like going back to pre-calc. It's a nice technique. Whenever you see something that looks like this, you can attempt to complete the square, put it in its vertex form, and then it's easy to plot. So yeah, just based off of your looks, I should probably do this. Okay, so We want to know the extrema, these minimum maximums on that closed interval. We know that they exist because it's continuous. But to get a picture and to get a better sense of what's going on, we should just draw it since it's just a parabola. And the way that we're going to do this, complete the square, vertex form, then it's easy to draw. So let's consider, okay, so f of x, I'm just going to write it out what it is. So f of x is equal to x squared minus 4x plus 5. And the way that completing the square works is you have x squared plus b times x plus c. You half b divided by 2 and then square it and then add and subtract. Do y'all remember this? Like, I'm going to take up too much room and just get rid of this. Again, this is completing the square. This is not calculus. This is just a algebra technique. So if you have like y is equal to x squared plus bx plus c, like that, this is like saying x squared plus bx plus b over 2 squared minus b over 2 squared plus c. Notice I just added 0, nothing happened, right? And then this right here is factorable. That's the whole point behind completing the square, right? What times what equals that, that adds to that. It's precisely b over 2. So then this is equal to x plus b over 2 all squared minus whatever this other stuff is. I don't know what those numbers are. I can't combine them, like whatever. But like, that's the whole point, to put it like that. You divide b by 2, square it, and add that value and subtract it to the equation. You can always add and subtract the same thing to an equation. It doesn't change because you can always add 0, right? So what's b here? It's -4, right? So this will be equal to x squared minus 4x plus -4 over 2 all squared plus -4 over 2 all squared plus, oh no, sorry, minus. You have to add 0. That was almost a big mistake. So like that and that is equal to 0, right? So that means the equation didn't change, right? So then this becomes x squared minus 4x. So -4 over 2 is just -2, right? Like that. Is the door locked? Okay. So, all right, now we can just do some more algebra here. We already know the answer, but I'm just walking you through every step, so it's okay. Again, you can like clearly see that this is 0 right here, right? But the whole point of us doing this was to look at this business right here. Is that factorable? Yes, right? What times what equals 4 that add to -4. -2 times -2, right? Precisely that b over 2, right? That's the whole point. So this will be x minus 2 all squared and then plus 1. That factors to x minus 2 times x minus 2. And now it's really simple to draw. Is it? I don't know. That's the vertex form, by the way. So I'm very careful. All right, so 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, whatever. Okay. So this is the parabola. It's been shifted to the right by 2 and then raised up by 1. And then it's just a normal parabola. So shifted over by 2, raised up by 1. There's the vertex right there. The vertex is when occurs when this is equal to 0, right? X equals to 2. And then looks something like this. And then on the other side, so where is the y-intercept? Did I do this correctly? Yeah, so if I want to find the y-intercept, what do I do? I set it equal to 0. Move the 1 over. Yeah, that's not going to work because I'm at the square root of -1. I'll just draw it symmetrically like this. I'm pretty sure I know where it occurs. That, something like that, whatever. Okay. So we can clearly see where a minimum occurs, right? Clearly. We know it's a parabola, we drew it. The minimum occurs at where? So f of 2 equals to 1 is a minimum. It's like on that interval -1 to 3. That's just clear from the picture. Okay. But as we look to the left and right, we're on a closed interval. So like the -1 2, 3. My drawing is a little bit off. It's hard to tell which one is higher, right? Like the function's value exists. Right? Maybe I drew that, whatever. But the function's value exists there. Which one is higher? It looks like with my terrible drawing, -1, like f at -1 would be higher. But we can find out, right? We know that it's kind of like a bowl, right? So we know that we're increasing that way and increasing that way. So the largest will be going this way occurs right there. And the largest will be going that way occurs right there. So we just have to look at them. So what's f of -1? So what does this become? -1 minus 2 is -3 squared, 9 plus 1, 10. And then what is f of 3? That is a perfect 3. So put in a 3 there. Yeah, it's easy to see now. It's just 2. So this right here, that is a maximum. On -1, 3. So this kind of hints at a technique that we're getting to in probably like 15 minutes or so. Right? The function is continuous on that closed interval. So we for sure need to evaluate the function at the endpoints of that interval, right? That's like, we know that those could possibly be maximums or minimums, right? Also, we need to know when something like that happens, right? Like, why am I doing that? Can someone guess? Well, yeah, but why am I literally just doing this, like horizontally? What's the slope of the tangent line right here? It's 0, right? So we need to know when that thing is doing this, right? Changing from decreasing to increasing, which has to happen when the derivative is equal to 0. Or like something like this happens. So this would be like f of x equals to the absolute value of x, right? Does the derivative exist there? We've mentioned this once before.
Yes.
It does not. Because the derivative is equal, so let's think about that for a moment. Let's consider that, so this is like a smooth version of the absolute value function, right? And this one does have a derivative, which would tell us, I mean, like the derivative is equal to 0 right there, which tells us that we're like changing, right? So what's the analogy here for that crimp? So if we were trying to find the extrema or minimum and maximums of f of x equals to the absolute value of x on -1, this is like a very similar problem, right? We know the minimum, we know that the minimum is going to be occurring right there. But unlike this one, right, like we could, if we needed to, we could use the derivative here to tell us that there's something happening of interest. That is not so much the same. So in order for, so what does it mean to have the derivative? So, okay. So f prime of 0, right? F prime of 0, that's where we're like kind of considering that, right? So what does that equal to? That's equal to the limit as the change in x goes to 0 of f of x plus delta x minus f of x over. So right, that's the formal definition that we learned a long time ago. Okay. Now, how could we define this, right, with the absolute value? Well, recall that a limit exists if and only if the limit from the left-hand side and the limit from the right-hand side, they meet at the same value, right? And the function is evaluated, like you can evaluate it at that value, right? And you don't have to evaluate the function, I'm sorry. If the left and right-hand side limits equal each other, right, and exist. So maybe we can look at like, okay, if this exists, we don't know yet, we should maybe consider the limit as the change in x goes to 0 from the left. F of x plus delta x minus f of x over delta x, right? We need to be very careful here. So again, the derivative is not telling us where the function is going, right? The derivative is telling us the slope of the tangent line, right? Where it's going. On the left-hand side, as we're approaching 0 from this side, what's the slope of the tangent line? To any point on the left-hand side. Say it louder.
Negative.
It's negative, but it has a value too. -1. Right? Well, maybe it's easier on this side. What's the slope over here? It's just 1, right? Because it's just x. You know, on this side, it's -x. Right? So the limit from the left-hand side of this ratio is telling us that tangent line, right? So this will be -1, right? But if we look at the limit from the right-hand side, again, notice I'm not actually computing anything like I could, right? On the left-hand side, it would be equal to something, on the right-hand side, it'd be equal to something else. But just looking at the figure, we know what the tangent lines are, where they're going, right? the tangent line always on the left-hand side is going to be -1. The slope of it, I mean. On the right-hand side, it's always going to be +1. Okay? No matter how close we get to that value. So, I'm tempted to like work it out like the actual limit, but hopefully you understand the concept. Okay, so does this equal that? No, which means that this doesn't exist. So if that's our f prime of 0 does not exist. It tells us nothing about maybe that, right? But maybe it does tell us something, right? If it, like, what are the possibilities for the limit of a function to like not exist, right? Like from the left and right hand side. Like it could be like division by 0 or something weird. It still tells us that we might need to investigate the place where the limit doesn't, the derivative doesn't exist, right? Because one possible case for the derivative not to exist is when you have a change in slope like this, right? Positive, negative to positive, which means that we did kind of, maybe we were at a minimum right there. So we need to check if this is a minimum of that function over that interval because the limit doesn't exist. Does that make sense? Like, think about it, like something like that, the tangent lines from the left and right hand side are not going to match as they approach whatever this value is here, C. Right? So, but that's all, that's a possible crimp in the graph where like that could be a maximum in that case. So we should check it. And this has like a formal name. I think I'm ready to write those out. Yes, I'm ready for the definition of that. Okay, so definition. So let f be defined on, defined at C. Okay. F is just defined at some point C. Okay. So if f prime of C is equal to 0, or if f is not differentiable at C, then C is a critical number of F. Meaning that something is changing with the graph of the function at that value C. Okay, the graph could be crimped, like at the absolute value, or it could be changing direction smoothly, like the parabola that we saw. Okay, so with that being said, with this definition, let's list out a technique for finding minimums and maximums of a continuous function on a closed interval, right? Again, recalling the extreme value theorem, we know minimums and maximums are going to exist for continuous functions on closed intervals. So we can find them, right? And this is the following technique. So finding, I'll call them extrema. I've been using that word anyhow. I don't want to write out minimum and maximum anymore. So finding extrema of a continuous function on a closed interval. There's like a nice step-by-step method for doing this. With part one, find all critical numbers. Okay. 2, evaluate f at each critical number. Okay. Part 3. Evaluate f at each endpoint of the closed interval. And then part 4, that's the simplest one. The smallest and largest of these values are the minimum, parenthesis S, minimums, it could be more than one, and maximums. And could be of f on the closed interval. Okay. Which we've already kind of done in a sense with the parabola, right? With in the absolute value function. Okay. Sort of like we intuitively were doing that. When I drew the parabola, you saw that, oh, it's changing at the vertex, right? That's like saying that the derivative is equal to 0, right? When I drew the absolute value and the derivative didn't exist at 0, that's like the function changing right there. It's a possible minimum, right? So intuitively, we were already kind of doing this. Now it's just kind of formally written out so that you can easily do this for your homework. All right, so here's an example problem. So, okay, does the function f of x equals to 3x to the power 4 minus 4x cubed have minimum and or maximums on the interval -1 and 2, and if so, find them. Okay, now I feel like this is a good problem. It should be easy to find derivatives, extremas, critical numbers, whatever. It's a good starting point. You have that list written up. So I'm going to give you like 10 minutes or so to work on this problem. And I'll pause the video while you're doing so. Okay, so let's go ahead and look at the solution all the way through. Now, notice that this problem has two things, right? Does this function have minimum and or maximums on that interval? And if so, then find them, right? So the full solution actually is two parts. First, we need to answer the question, the first question, right? Now, does that function have minimum and maximums on this interval? Yes. So we can say why though, right? There's a reason, and it's by this extreme value theorem, right? So we can say, since f of x equals to 3x to the power 4 minus 4x cubed is continuous, on this closed interval -1 to 2, the extreme value theorem implies yes to the first question. Okay. So now we need to answer the second question. Okay. So, which is this table right here, right? So we need to find all the critical numbers, which means we need to find the derivative, right? We have to. So let's just note that f prime of x is equal to what? 12x cubed minus 12x squared, right? Now, oftentimes when you want to know when an equation is equal to 0, it helps to factor things, right? So I see common factors all over the place. So we have factor out of 12, factor out of x squared, and then we're left with x squared minus 1. Okay.
Isn't it just x?
Oh yeah, it's just x minus 1. Thank you. Okay, so this derivative exists everywhere, right? It's a polynomial. There's nothing to worry about. No matter what we try to plug in, that derivative exists. So we just need to find out when it's equal to 0. And there's only two options, right? So looking at that equation, it's easy. F prime of 0 is equal to 0, right? And then when x is equal to 1, it's equal to 0, right? That's why it helps to factor when setting an equation equal to 0. Because as soon as one of the factors is equal to 0, you're done, right? So if that's 0, you're just done. Okay, so those are the critical numbers, right? So this would be like part 1 of that list. Part 2, we need to evaluate f at each of those values. Okay, so the original function evaluated at 0 is equal to 0. And the original function evaluated at 1 is equal to -1. Okay. Then part 3, you have to evaluate the function at the endpoints of the interval. So f at -1. Okay, so let's just be careful and actually plug it in this time. 3 times -1 to the power 4 minus 4 times -1 cubed. Okay. Now, any even power, a negative to an even power is just positive, right? So this will be just 3. And then this, a negative to an odd power is negative. So it'd be negative times a negative would be +4. So this is equal to 7. And then the other endpoint, oh, my leg is about to fall off. 2, so f at 2, 16. Can I trust y'all? Do I get more than 116? All right, so that'd be 16. All right, so then part 4, we have all these things to choose from, right? We have 7, 16, -1, and 0, right? The minimum is the minimum of the function over that interval. The maximum is the maximum. So f of -1, I can just say is like minimum. Oh yeah, sorry, f of 1 equals to -1, right? So this is a minimum. And then f of 2 is the maximum. I don't like that arrow. I'm going to say, I'm just going to write with words. I like to be clear. The arrow isn't clear. f of 1 is the minimum. And f of 2 is the maximum. Okay. Nice. Okay. Now I want you to like notice something though about what we've learned by finding this. Just like, yes, I have an idea about what that looks like before doing any of this, but I doubt any of you had an idea about what that looks like before doing anything, right? This information tells us, could help us kind of get an idea to sketch it out. And it's actually one of the sections in your textbook. So like using this information, let's see if we can get an ugly looking sketch of the graph of that thing. And not that, I mean the graph of the original equation here. Yeah.
How come we have to get the derivative of it first?
Because that's how we find the critical numbers, right? The critical numbers are when the derivative is equal to 0, i.e. we're changing direction. If the derivative does not exist, then we have like this maybe crimped thing that we have to check on. That's telling us the changes when the function is changing from positive to when the function is increasing to decreasing or decreasing to increasing or neither maybe.
Mhm.
It's telling us something is happening when the derivative is 0 or does not exist. All right, so let's see if we can just get a rough guess, and I'm not going to say that this is a good drawing. I'm just going to say, using this information, let's try to draw this thing and get a sense of its behavior over that interval. And it's just a rough guess, right? So here's like -1, and we're going to what? 2. Like over here. Right? So we know the value at -1, it's like 7, right? So it's like maybe there. Okay. And we know the value at 2, it's 16. It's like up there, right? We also know that that is the maximum, right? So we know that the graph of this function is never going to go above that line on that interval, right? So we know it's never going to go above, right? So then we also have these values where the derivative is equal to 0, right? So maybe like at 0, right? What's the function's value at 0? It's 0, right? It's like right there. Okay. So we know that the derivative at 0 is equal to 0, right? So we know something. We know the slope of the tangent line, which I'll draw in blue, is like that. We know that's what it looks like there, right? And we know we're coming from up there, right? So somehow, like, and there's no other places where the derivative is 0 in between here and there, right? So we know that starting from there, it's continuous. It has to connect there somehow. So maybe like that. I don't know. Okay. And it has to flatten out right there. Now, what's the other point? 1.
Which is -1.
Why did I write? That should be here. Right? Yeah, like the derivative at 1 is 0. Sorry about that. So at 1, so what's the value here? -1. So it's like down, right? Okay. So then, is this thing going to go like this in between here? It can't, right? Because that's the only place where the derivative is equal to 0, in between there and there, right? So it has to kind of go like that. It has to. It can't, because how would it get back down, right? So it has to kind of do that. And then the derivative here is 0 as well, right? Which means that the slope of the tangent line looks like that, right? Which means that when we hit this part, it's going to be flat like that. And we need to somehow get up there really fast. And there's no other place where the derivative is 0 in between there and there, right? So that means to me that it's going to shoot up like that. Is that kind of what it looks like? Did anyone graph it? It looks like that.
Yeah.
Right. So again, without knowing what this looks like, and like, just imagine trying to plug in number by number by number to get that graph, right? Of that. It's much easier to know where there's extreme changes happening, where the derivative is equal to 0 or it doesn't exist. That tells us something like about what is changing. And because it's continuous and there's no other places where it's going to change, I know that it's going to connect through there like that. And then since there's no other places in between there and there where the derivative is 0, I know that it has to kind of do that like S shape. Yes, question.
Yes. What's the plan with number 2 to evaluate f in the regular function?
Oh, because we have to evaluate the function at the endpoints, which I'm glad that we did, because f at 2 is the maximum value of the function on that interval. Right, f of 2 is what, 16?
So basically, it's just finding y.
Yeah, it's finding the output, right? The y value is what we're concerned with, the minimum, maximum values of the function over this interval. Maximum, minimum, and we also got some information about the shape by looking at the slopes of the tangent lines given by that. Right? Again, if we wanted to be more precise, I suppose like We could take it, find a derivative right here and look at how steep this curve is. Find it right there, how flat is it, like a little bit to the right. The derivative, if you think about it, like take the derivative there, that's the slope of the tangent line there. Take the derivative there, that's the slope of the tangent line. Take the derivative there, slope of the tangent line. Take the derivative there, slope of the tangent line. Do you see what I'm doing? It will create the graph. In fact, doing that, it has a name, it's called Taylor's theorem. You can recreate the function just based off of the derivatives. Right? You can create the graph of the function, you can look at it by knowing the rate of change of the function if you just measure it. Right? So this happens in science where you have a measurement that's changing in time at a certain rate, that's the derivative, and you want to know what the function looks like that's like describing the phenomena. You can just use those rates of change, which are the derivatives, and piece them together, and you're getting like an approximate to the function that you're seeking. Okay. Now, all right, so, yes.
This might be a silly question, but for f of 2, it won't be a local maximum, right? Or would that be considered a maximum?
Yeah, this is a maximum on this interval.
It would still be considered?
It's a maximum on an interval because the maximum means the possible values of the function over anything in that interval, right? Now, here, there's no interval around 2 for where there's a little cusp. So this would not be like a local maximum of the whole function. Only when there's an interval around on both sides where the derivative is 0, where you can you say that?
So-
Here, it's just on this interval, out of all of these possibles, that's the biggest thing that gets spit out.
So we could consider that as the local maximum for this interval.
That is the maximum for this interval. That is precisely the maximum for this interval. Okay. All right. So again, this is the process. Now, in general, I think if you know the differentiation rules, I think this kind of stuff is pretty simple. You just have to be very procedural about it and careful. The only time that I've seen students run into problems, provided they're familiar with the rules, is when it comes to finding where the derivative is 0 or doesn't exist for these trig functions. Right? So let's consider this problem here. I have to squeeze this in because you need to see this at least one time. So find the minimum and maximums of f of x equals to 2 sine x minus cosine 2x on 0, 2 pi. Okay, so I just heads up, because we're running out of time, I'm going to move relatively quickly on this one, but you can always watch the YouTube video and put it on like half speed. So you'll be able to, you have the information. Okay. All right, solution, it has minimums and maximums because it's continuous on that. We don't even need to say that. It didn't ask us to. So we just need to first find the derivative. All right, so f prime of x is equal to 2 times cosine of x minus, you have to use the chain rule here. Derivative of the outside is negative, what? Negative sign, right? Of 2x, like that. Times the derivative of the inside. Oh. So yeah, so that's the outside times. Oh, sorry, I put a 2 there. Okay. Okay, so negatives go to positive, right? And they have a 2 out there. 2 cosine x plus 2 sine of 2x. Okay, so you won't have to worry about this as much in my class as maybe like a Cal 2 class, but this has a nice form. So you just have to recall from the table in the front of your textbook this identity. So sine of 2x is equal to 2 cosine x sine x. And the only reason why I'm recalling this identity is because it's going to make it easier for me to determine when these things are, when this whole thing is equal to 0. Because I can factor out a cosine, and that's when it's easier to find the zeros, right? I said that earlier. If you can factor, then it's easy to find when the derivative is 0, or when any equation is 0. So if we're calling this identity in this, I get that the derivative is equal to 2 cosine of x plus 2 times this business here.
2 cosine.
Right, so it'd be 4 cosine x sine x. Like that. Okay, so now I can factor out a 2 cosine x. So 2 cosine x times 1 plus 2 sine of x. Okay. That's the derivative in its factored form using this identity. Now we can figure out what x's make this thing equal to 0, because those are the critical numbers. So basically what we want to solve is this. So 0 is equal to 2 cosine x times 1 plus 2 sine of x. This actually isn't that bad. Okay, now we have a product, so we can split this up into 2 equations for solving when this is equal to 0, right? If this is 0, good. If that's 0, good, right? So let's just write this out. 2 cosine x equals to 0. Well, on the interval 0 to 2 pi, there's only 2 places this occurs. X is equal to pi over 2. And 3 pi over 2, exactly. So when x is equal to that, that's equal to 0, which implies this whole thing is equal to 0. Next up, this one. Which means we want values of x when this is true. Okay. Now this is probably throwing you off. If you had a calculator, you might get lucky. But if you didn't have a calculator, you have to remember this unit circle. Right? So unit circle, it's gross, but whatever. I just have memorized the angles for sine and cosine in between here and there. If you know those basic ones, like pi over 6, pi over 4, pi over 2, 30, 45 degrees, 60 degrees, if you know those, then you know all of them. So if you can just remember them in there, you're good. Why? Because, well, in this case here, so I know that sine of pi over 6 is equal to 1/2, or 30 degrees. And then pi over, so it's pi over 6, then pi over 4, which would be, root 2 over 2, then you have pi over 3, then you have pi over 2. If you know those, you can figure out the rest. So I know that. But because the unit circle is symmetric, right? And the y values are the sine, I know that the negative of that is that's going to be negative 1/2. So what is that? That's 2 pi minus pi over 6. right? So 2 pi minus pi over 6. Yes, 11 pi over 6. That's one of them, right? But it's also symmetric if I wrap around all the way over here. So that, the y value there is going to be a half as well, right? Ignore the x value. Okay, the y value there is a 1/2, y value there is negative 1/2. So that means that here, whatever angle that is, the y value is going to be negative 1/2. So what is that? That's pi plus pi over 6, right? Pi plus pi over 6. So then that's one right there, and then pi plus pi over 6 equals 7 pi over 6. Okay, so there. Those are the critical numbers. Okay. And again, we're restricting ourselves to in the interval 0 to 2 pi. That's why I didn't just do negative pi over 6. That's not in that interval. I can only pick in here. So those are my critical numbers. I like using this notation when I have a bunch of them. C equals to like the set of pi over 2, 3 pi over 2, 11 pi over 6, and 7 pi over 6. Okay, so those are my critical numbers. So next, I need to evaluate the function at its endpoints. So then f at 0. Oh no, I have to evaluate the function at each of those, right? I find the critical numbers. That's like part 1. And then part 2, I need to evaluate the function at each of those values. So f of pi over 2 is equal to what? 1 minus 0, so it'd be just 2, right? F of 3 pi over 2, it's going to be negative 1, 0, so it'll be negative 2. F of 11 pi over 6. Okay. So the y value here is what? So this point right here, the y value is 1/2, and then the cosine value, yeah, √3/2, right? So at 11 pi over 6, that's right there, it'll be √3/2 comma negative 1/2, right? So 2 times negative 1/2 minus the cosine of 2, that, so it's just cosine of √3. Whatever that value is, if you had a calculator, you'd plug it in. So we did actually run out of time. You would calculate that number with a calculator. Like it's just a simple scientific calculator is good enough. You would calculate this number. You would calculate the endpoints. And then the minimum and the maximums of those numbers would be the minimum and maximums of the function on that interval. But again, you should be familiar with the base angles inside here to here for cosine and sine. That way you can solve this here. And that will be it for today's lecture.